The philosophical argument of my idea, and now by extension hypothesis, regarding how and why our universe came into being is based on one key assumption. That is, fractal geometry is the underlying cosmological principle as opposed to the spatial distribution of matter in the universe being both homogeneous and isotropic. A self-similar pattern with respect to fractal geometry is an object that is exactly or approximately similar. That is, the whole has the same shape as one or more of the parts that make up the whole. Scale invariance is an exact form of self-similarity where at any magnification there is a smaller piece of the object that is similar to the whole. The hypernova of a massive star that gives birth to a black hole while releasing a pair of gamma-ray bursts is the second largest explosion in the universe. Second largest because the Big Bang event that gave birth to our universe was the largest. Marrying the idea of self-similarity of fractal geometry with the physical process of a hypernova gave rise to my idea. Was the Big Bang in actual fact a kind of supernova following the same physical dynamics as an exploding star? Imagine a star-like object outside our existence, so massive that it contains all the matter in the universe, but star-like nonetheless. As a guide, the unexplained presence of the Boots supervoid, whose spherical shape has a diameter of 330 million light-years across, is such a star-like object, I would conjecture. Otherwise, if not, then why is it so spherical? And in a universe that is so homogeneous and isotropic, why does this supervoid, this massive nothingness that occupies 0.27% the volume of the observable universe, exist? In order to understand my idea, I first need to describe the physical process of a hypernova, the second largest explosion in the universe, aside that from the Big Bang event. Every star begins its life as a huge cloud of dust, primarily composed of hydrogen, drawn together by the force of gravity. The pressure and temperature at the heart of the protostar, coming from its gravitational weight and friction, becomes so large that the atoms begin to fuse together, starting the nuclear fusion process. At this point, a star is born, as the nuclear fusion process at its core comes to life and it shines for the first time. Hydrogen fuses to helium. Helium fuses to beryllium and carbon. Carbon to oxygen, and so on to form all the other heavier elements. In other words, all the atoms that make up your body and the world around us were formed in the heart of a star. We are, quite literally, star stuff. There are two primary forces working directly against one another that determine the shape and size of any star. The first inward force comes from the gravitational mass of the star, where the direction of that force is in towards the core. This is what gives rise to the incredible temperatures and pressures at the core, where the atoms are fused together because of this gravitational force. The energy released from the fusion process gives rise to the second outward force. This outward force comes from the energy released from the fusion of atoms at the core. This outward force, in turn, counterbalances the inward gravitational force, the equilibrium of which determines the shape and luminosity of the star over the course of its lifetime. For the vast majority of a star's life, the primary fusion process is of hydrogen into helium. But every star has a finite amount of hydrogen, and eventually this will run out as the star comes to the end of its life. So when all the hydrogen fuel in the Sun has been converted to helium, then the fusion of helium becomes a dominant process. This change in the fusion's fuel source creates a new distribution between the two aforementioned competing forces. How a given star dies or goes supernova is dependent on how the two competing forces are redistributed when its hydrogen fuel source is depleted. In the case of our own Sun, around 4 to 5 billion years from now, this redistribution in the hydrostatic equilibrium will cause our Sun to swell up into becoming a red giant. This expansion of our Sun into a red giant will engulf the planets of Mercury and Venus while burning Earth to a cinder. In turn, huge clouds of plasma and gas are ejected from our dying Sun, leading to the formation of a planetary nebula. Eventually, the helium fuel will run out and heavier elements will come to dominate the fusion process. When iron comes to dominate the fusion process, there is a critical and extremely explosive change. Unlike the fusion of lighter elements, which produce energy, the fusion of iron rather consumes energy. This consumption of energy caused by the fusion of iron turns the outward fusion force in on itself. This turning of the fusion force inwards, coupled with the inward gravitational force at the core, triggers the catastrophic explosion that we call a supernova. The force from this colossal inward implosion at the core fuses the remaining material together. Depending upon the size of the star, this inward implosion forces any space between particles out and gives birth to white dwarfs, neutron stars, and even black holes. A white dwarf, composed mostly of electron-degenerate material, is so dense that a single teaspoon would weigh a ton. Even denser still, a neutron star where the core has collapsed beyond the point of the atom and into its nucleus. Electrons fuse with protons, becoming neutrons, hence the name, a neutron star. A teaspoon from a neutron star would weigh around 1 billion tons.